Hello class. Today we shall be talking about solution stoichiometry. I would like to give a brief review on basic stoichiometry, the concept of limiting excess reagents, and finally, reactions in solutions. First, let's talk about basic stoichiometry. Stoichiometry refers to the mole to mole relationships in a chemical reaction. Suppose we have the following hypothetical reaction. A plus 3B will produce 2C. This means that 1A will react with 3B to form 2C. Furthermore, this can also be interpreted as to form 2C, we need 1A to react with 3B. In the case of chemical reactions, let's have for example 1 mole of sodium hydroxide will react with 1 mole of hydrochloric acid to produce 1 mole of sodium chloride and 1 mole of water molecule. This can be interpreted into many different relations such as 1 mole sodium hydroxide is to 1 mole of hydrochloric acid is to 1 mole of sodium chloride. So you can make any other ratio based from this relation. Let's have a brief example. Typically in stoichiometric problems or problems involving stoichiometric calculations, usually the thing that is given is the mass of one reagent. For example, mass of sodium hydroxide is given such that it reacts with another amount of the other reagent, and we need to find the amount of the product produced. So suppose the mass of hydrochloric acid is excess. And finally, what we want to find here is the mass of sodium chloride. What do we do here? Our strategy would be to convert the mass of sodium hydroxide to moles of sodium hydroxide and convert it to moles of sodium chloride, and finally convert moles of sodium chloride to mass of sodium chloride. How do we do the first step? We can do it is molar mass of sodium hydroxide. The second one is the mole ratio from your chemical reaction or from your balance equation. So it is necessary to have a balance equation in order to solve stoichiometric problems. The solution would look like this. So this one is your molar mass. Cancel out the unit and you will get moles. Then we can now use the mole ratio from the balanced chemical equation. 1 mole of sodium chloride is to 1 mole of sodium hydroxide. And finally, cancel out the unit and we'll convert the moles of sodium chloride to mass of sodium chloride using the molar mass. Finally, cancelling all the units, we get the final answer, which is 58.45 grams of sodium chloride. This is the most common problem that is given in basic stoichiometry. Take note that in this type of problem, one of the reactants is designated as excess. But in the actual scenario, we are usually given the amounts of starting reagents or the reactants, and we need to figure out the limiting reactant in the reaction. So basically, what is the limiting reactant? The limiting reactant is the reagent that is being exhausted first in a reaction or is being consumed in the reaction. Let's have an analogy for what a limiting reactant is. Suppose in a class there are 20 boys and 30 girls. The class would then go to a JS prom. Thus, the boys and girls need to pair up for the social dance. Based on the number of boys and girls in each class, the number of boy-girl pairs for the social dance is limited. And the one that limits the number of boy-girl pairs is what we call the limiting reactant in the case of chemical reaction. So in this context, the limiting reactant are the boys because there are only 20, and the excess reactant are the girls. So in cases like this, I make use of what we call the IRA table, or initial, during the reaction, and after the reaction. So in this case, in the initial part, The teacher have not yet directed the class to pair up for the JS problem, whereas in the reaction phase, the teacher has already designated the class to pair up. So now, since in the pairing up, all the 20 boys are paired up to only 20 girls, producing 20 pairs for the social dance. So after the pairing up, we only have 0 boys remaining here. Everyone has been paired already. Whereas for the girls, there are 10 unpaired girls remaining and 20 pairs that have been produced. So this is the context of limiting reactant. This analogy can be used in many types of reaction. Suppose we want to have another type of pairing. If 20 boys and 30 girls in a class, the teacher instructs the class to pair up one boy with two girls to make a trio for the singing project. Which of the following is the limiting reactant then? So let's start with our strategy. Using the IRA table, initially there are no pairs, or there are no triads. How can we determine which one is the limiting reactant? The answer is we should determine the maximum number of trios that can be formed using this number of participants in the class. So if we use 20 boys, now we have to use the ratio. So one boy will produce one trio. So we can only have 20 trios using this. On the other hand, if we use the number of girls that are present in the class, how many trios can we produce? The answer is only 15. The group that produces the lowest number of trios determine the pairing up rate. In this case, it's the girls who only forms 15 trios. So they are the ones who dictate the pairing rate. That means the girls are the limiting reactants. In this case, all the girls are paired up. Boys pair up with 30 girls then to form 15 trios. So after the pairing up, we have 5 boys remaining. All the girls have paired up or have grouped together, and there are 15 trios that have been produced. Okay, these are the two of the analogies that can be used in understanding the concept of limiting reactant. Okay, let's apply this to chemical reactions then. Suppose the amount of sodium hydroxide is given. For example, mass sodium hydroxide is 40 grams. And also the mass of hydrochloric acid is also given, 35 grams. What is asked is the amount of sodium chloride produced from the reaction. Since the amount of both the reactants have been given, we have to determine which one of the reactants is the limiting reagent or the limiting reactant. How do we do that? We can do that by converting everything to moles and using the IRA table that I have discussed previously. In the context of the reaction, the moles of sodium hydroxide is just using the molar mass. You can calculate that there is 1 mole of sodium hydroxide that is present. Also, we can convert the amount of hydrochloric acid to moles of hydrochloric acid using its molar mass. Now we can use the IRA table for this. Initially, there's 1 mole of sodium hydroxide and 0.96 moles of hydrochloric acid. There are no moles of product initially. During the reaction, the first that is exhaust is the one with the least number of moles. So in this case, the least number of moles, which is the limiting reactant, then is the hydrochloric acid, producing this amount of 0.960 mole for the product. After the reaction, the remaining sodium hydroxide is 0.040 mole, and there are no remaining hydrochloric acid since they are all exhausted. Finally, we can calculate the amount of sodium chloride that has been produced from the reaction, which is 0.96960 mole. We can convert this to mass of sodium chloride using the molar mass. So 0.96 moles of sodium chloride multiplied by the molar mass of sodium chloride, which is 1 mole is to 58.45 grams, which gives us a value of 56.1 grams of sodium chloride. And that is by using the IRA table, this one. The other method is by calculating the moles of product produced. In order to get the limiting reactant, calculate the moles of product using the data that has been given. So from the reaction, we have already calculated the moles of each reagent. So for the sodium hydroxide, moles of product, so we use the amount given by sodium hydroxide, the amount of sodium hydroxide that is present, which is 40, multiplied by its molar mass, which is also 40, and converting or relating it to moles of sodium chloride, which is present using the mole ratio. So finally, you get 1 mole of sodium chloride. Next, calculate the same amount of product using the amount of hydrochloric acid that is given. The amount given is 35 grams of hydrochloric acid, and by using the molar mass, we can calculate the moles of hydrochloric acid that is present, cancelling out the units, and we can relate it to the moles of sodium chloride using the mole ratio. The final answer will then be 0.96 moles of sodium chloride. Remember that the reagent that produces the least amount of product is the limiting reagent. So in this case, the limiting reagent is the hydrochloric acid since it produces the least amount of product compared to sodium hydroxide. Finally, we can calculate the mass of the product using the moles of product calculated. So the moles of product calculated, this one, is just this calculation. So you will have the same answer afterwards. However, in the laboratory, we often do not use pure hydrochloric acid, pure sodium hydroxide, or pure hydrochloric acid since these reagents are very corrosive. Corrosive means it is very reactive and can be dangerous to one's health. In order to mitigate the risk of utilizing these chemicals, we set up a reaction of these chemicals using solutions of these reagents themselves. So we use solutions when setting up chemical reactions. So in the actual scenario, we use solutions of sodium hydroxide and hydrochloric acid. So since we are dealing with solutions, most often the concentration of sodium hydroxide is given and also its volume. Same with the concentration and volume of hydrochloric acid. Take note that both the values of the sodium hydroxide and hydrochloric acid are given. This means that we have to determine which one is the limiting reagent. So how can we determine the limiting reagent? The answer is, first we have to convert everything to moles. How can we convert everything to moles using this data? So take note that molarity is basically moles per liter. When we multiply molarity with volume in liters, we can cancel out the liters and it leaves us the value for the moles. So in this case, in order to calculate the moles of sodium hydroxide and moles of hydrochloric acid, we need to multiply it by its volume. We need to multiply the concentration of sodium hydroxide by its volume and the concentration of hydrochloric acid to its volume. Take note that the volume should be in liters in order to cancel out the units. So what we have here is 0.5 moles of sodium hydroxide and 0.375 moles of hydrochloric acid. Now we can use the IRA table or the other solution that I have taught you. Using the IRA table, we can supply the amount of reagents in the table in the initial part. Initially we have 0.5 moles and 0.375 moles here. We don't have products yet at the start of the reaction, but since this is a solution, so meaning everything is water, that means we don't have to account the water here. So looking at the amount of reactants present, we can immediately see that the limiting reagent is the hydrochloric acid, since it has the least amount of moles, and it also means that it is the reagent that is exhausted first or the limiting reagent. So minus 375 during the reaction is 0.375 here. And finally, we produce 0.375 moles of sodium chloride. After the reaction, we have 0.125 moles of sodium hydroxide remaining, nothing of hydrochloric acid remaining, and 0.375 moles of sodium chloride remaining. If you are asked what is the molarity of sodium chloride after the reaction, we can then calculate the molarity using the moles of sodium chloride produced and also the total volume of the solution. So in this case, we added 500 ml, which is 0.5 liters, plus 300 ml, which is 0.3 liters. So it's basically 0.375 moles over 0.8 liters. Then we can calculate the molarity of sodium chloride after this calculation, which is 0.375 over 0.8, 0.469 molar of sodium chloride. The other solution that I introduced previously is calculating the moles of the product using the values of each reagent. So in this context, you can calculate moles of the product by sodium hydroxide, and that is basically the amount of sodium hydroxide in this solution is we have 1 moles per liter of sodium hydroxide reacted with 0.5 liters of sodium hydroxide. So that gives us mole of sodium hydroxide. Then using the mole ratio, we have 1 mole of sodium hydroxide, which produces 1 mole of sodium chloride. So finally, we have 0.5 moles of sodium chloride produced. On the other hand, we can also use the amount of hydrochloric acid to calculate the moles of sodium chloride produced. So what we have is 1.25 molar or moles per liter multiplied by the volume of hydrochloric acid used, hydrochloric acid solution used. Cancel out the units and we get moles of hydrochloric acid, and then multiply it by the mole ratio. Cancel out the units and we get 0.375 moles of sodium chloride. In this context, the reagent that produces the least amount of product in moles is the limiting reagent. So that means the limiting reagent is your hydrochloric acid, since it produced the least amount of product compared to the other one. Finally, we can calculate the molarity of your product by this solution. So the answer is just the same. So what if we have another reaction and the ratio is not the same? Suppose we have this one. The molarity of sodium hydroxide is given, and also the molarity of hydrochloric acid, and also the molarity of sulfuric acid. How can we determine the concentration of the product? The answer is we have to convert everything to moles first. So same with the previous example, the moles of sodium hydroxide would then be 0.5 moles. In the case of sulfuric acid, we also have the same number of moles as previous example. But this reaction, take note that it has a different mole ratio compared to the previous reaction. So first we have to calculate which one is the limiting reagent and which one is the excess reagent using one of the methods that I've taught you before. So in this context, I can use the second method and also the first method. But I would like to use the second method this time. So using the value of each reagent. So first is moles of sodium sulfate by sodium hydroxide. So what we have here is we can use the moles of sodium hydroxide immediately. We have performed the calculation already. and make use of the mole ratio. In this case, 2 moles of sodium hydroxide reacts with produces 1 mole of sodium sulfate. So what we have here is 0.250 mole of sodium sulfate. Next, we can also calculate the moles of sodium sulfate by the values of sulfuric acid. We already know it's 0.375 moles of sulfuric acid, and making use of the mole ratio, we have 1:1, and we get 0.375 moles of sodium sulfate. Judging from the amount of product that has been formed, 0.25 is way lesser than 0.375, meaning the limiting reagent this time is sodium hydroxide. Now we can calculate the molarity of your product. Now we can calculate the molarity of the product using this calculation. We already know that there are 0.250 moles of sodium sulfate that is formed. Divided with the total volume, it is basically 0.5 liters plus 0.300 liters. So the final answer is 0.313 molar of sodium sulfate.